Good evening, everyone. Am I audible? Okay.
Yes, ma'am, you are audible.
Okay, so today we'll be discussing some assignment problems of previous weeks. Okay, so let's start with first question. Suppose K is some compact subset of Rn. So in Rn, how can we say that a subset is compact? A subset of Rn is compact if and only if.
Ma'am, every cover has a finite subcover, so
Yeah, but we have another property in Rn. So it is if and only if it is closed and bounded.
yes, ma'am.
And we are given that f is a smooth function. Then there we have the following options. First, f has local maxima and minima. At some point in K. Next, it says that f has global maxima and minima. At some point in K. Next, the derivative of f vanish at the extremes. And the derivative of f vanish at those points of extrema that are also the interior point. So this is all that we have already read in our graduation. So I hope this question you must be able to do because we know that if a function is smooth function means it is continuous, and continuous function defined on a compact domain always attains its maxima and minima. Therefore, it will have local as well as global maxima and minima at some point. So clearly, first and second options are correct. And what about third option? So the main difference between third and fourth is that they are talking about the point of extrema. So if we can take example, suppose we define f from close 0 to 1 to r, fx equals to x, suppose. So if third option was correct, clearly this function has minima at x equals to 0 and maxima at x equal to 1. So if third was correct, third option is correct. In that case, the derivative of f should vanish at 0 and 1. F dash 0 is equal to 0 is equal to f dash 1. But we can't say anything about the derivative at the boundary. Suppose this function was, if we extend this function to whole space R, in that case, we know that the derivative still won't be 0 at 0 and 1. It's 1 everywhere. So that's the first. If we had some extrema in the interior. So for a compact set, we know that the points lie either in the interior or on the boundary. So when we remove the boundary and we are talking about the interior point, then clearly we can define derivative. The function is differentiable over there. And we know that if a function is differentiable at a point and that point is extrema, in that case, it should vanish. So, but this gives us a contradiction. Therefore, the third option is incorrect. And if also we know that, therefore this third is incorrect. If a function is differentiable at a point at an extrema. Here the problem was that we don't know how to define derivative at the boundary points. We can find derivative of functions only when the point is an interior point of the domain. If a function is differentiable at its extrema, suppose x naught, then we know that its derivative should be 0. This does not hold conversely. That means being derivative 0 does not imply that the function has extrema at that point. Can you give me some example for that? I'm saying that x naught is extrema implies f dash x naught is 0. Yeah, if x naught belongs to some interior point of the domain, suppose k naught denotes the set of interior points. What about the converse part? Yeah, this converse does not hold. For that, you can take the example of the function fx is equal to x cube. If we define f from suppose -1 to 1 to r, fx equals to x cube. In that case, f dash 0 will be 0, but this 0 is not an extrema. We know that this is how fx equals to x cube can be plotted. That x naught is equal to 0 is basically it is a saddle point. Okay, so yeah, that's how we get from here we get our fourth option is correct. So yeah, this question must be easy for you. Let's move to next one. Consider the functions fxy. This is equal to x squared plus y cube gxy. So yeah, when we are talking about finding the quadratic form using some Hessian. So we basically take the Hessian at the critical points. Yeah, in previous session, I think we took both as variables. Yes. And also, I think there is some typing mistake in the question also. Statements. The quadratic form. Obtained using Hessian of these functions uh, are all 2x square. I think it should be 2x square. Maybe there is some typing mistake. Or you can just write an email to the professor if you want to confirm. Second, all these functions have critical points at 0. Then we have the function f has minima at 0. And okay, the function g has a minima. So I hope the using the exactly same procedure as we did in previous session, we can evaluate the quadratic form, or I'll do it for one. So, I'll do it for function f. So we have fxy equals to x squared plus y cubed. From here we have del 2f by del x squared will be 2, del 2f by del y del x is 0. And from here, del 2f by del y squared, this is 6y, and del 2f by del x del y, this will be 0. So yeah, firstly we should start with the critical points. Critical points, and del f by del x, this should be 0. This is 2x 0 implies x is 0, and we should have del f by del y equals to 0 as well. So this is 3y square 0 implies y is equal to 0. Therefore, we have just one critical point, 0, 0, origin. So we'll evaluate the Hessian at point 0, 0. So we have Hessian of f at 0, 0. This is del 2f by del x square at 0, 0. Del 2f by del x del y at 0, 0. Del 2f by del y del x at 0, 0. 12y square. So this is 2, 0, 0, and 6y and 0, 0, and also 0. And using this, we can evaluate the quadratic form to f xy. This is just xy, 2, 0, 0, 0. This will be 2x square. So yeah, similarly, you can find the quadratic form corresponding to the Hessian of functions g and f. In that case, also you'll get the same quadratic form. So eventually, our first option is correct. Yeah, clearly second option as well. So what about third and fourth? So do you have any idea?
Third one is wrong
How?
because if we take function y cube fxy equal to y cube, then as we go towards 0, then it will give positive and negative value about along y-axis, but f
Mhm.
has no local minima at 0. Means every neighborhood of 0, you can find
In
positive
the
and
neighborhood
negative.
of, yeah, exactly. The way we proved that some point is a saddle point.
Mm.
Earlier we did some problems related to this, no?
Yes.
Yes. And what about fourth option?
But the fourth one is right because g is always greater than equal to 0. So
Greater than equal to 0, and that is the value of g at origin.
0, 0.
Yeah. Also, you can see that this uh, q, yeah, but from this should also be a local minima, no? Because this is a positive definite function. No, this is not positive definite
Mm.
because we don't know about y. Mhm. So we don't know whether this is positive or negative definite. This is basically indefinite in all the cases.
No,
So we
but
cannot
whatever
use
is
the
the value of y is, this quadratic
yeah.
form gives greater than equal to 0.
Okay. We are saying that
Okay.
qfxy, this is 2x square. This is positive for every xy in R2. In fact,
Mm.
this will be 0. This will be 0 for all points of this form as well. So
Y, okay.
this is not positive definite, this is positive semi-definite. And as far as I remember, we have result for positive definite.
Mm.
If the quadratic form is positive definite, in that case we know that this is minima. But for positive semi-definite, we don't know, no? QF is positive semi-definite. In fact, for QF, QG, and QH as well. So we'll have to check what happens at 0. So for function g, clearly the function is always positive, which is the value. Function is always greater than equal to 0, which is the value at x, y, 0, 0. And for f and h, clearly you can find some path near in the neighborhood of origin. Yeah, similarly as we did earlier, to show that at some points the function might be greater than 0, and at some point it can be negative as well. So eventually, f and h will have saddle points at 0, 0. Okay. So next, consider the two parameterized curve. Is given by e to the power iota t and e to the power 2 iota t. So yeah, I think you all know the difference between both the curves. So e to the power iota t is just one circle. So we can consider it to be a spiral with just one circle, and e to the power 2 iota t is the spiral with two circles. Basically, they both are overlapping each other. So clearly, the functions are not same, but their range set. We can say that the range set is same in both the cases. So our first point was both curves are equivalent. They are not equivalent because we have kind of double length in case of e to the power 2 iota t. Both curves are equivalent. Then we had, yeah, both curves parameterize unit circle. This is correct. Because eventually the range set is same for both the cases. Unit circle. Then we have both have same length. No, because the this one has twice the length as this one, and I think that's the fourth point. So you can imagine the this function as, suppose we have two sheets and we are drawing circles on both of them. The first, so for t lying between 0 to 2 pi, sorry, 0 to pi, or the function f t equals to e to the power 2 iota t. So for t lying in 0 to pi, we are on the first sheet. We described the complete circle. And for as we move ahead, we are on the next sheet, which is exactly behind the first one. So yeah, in that way, whereas in the case of function e to the power iota t, we have just one sheet, and in the case of e to the power 2 iota t, we have two sheets. So that's how we can see the difference. Both curves have same length. This is wrong. And the third one says that the second curve has twice the length as the first one. Okay, so is this question clear?
Definitely.
Okay. So next we had a problem related to the method of Lagrange multiplier. So were you able to solve that because it was quite calculative?
No, ma'am, it seems to very complex.
Yeah, even I was having okay, we'll see that at the end. Let's discuss some other problems that we can do firstly. So yeah, let's move to the next assignment problem. Next we have some results related to step functions. Step functions are very nice functions. Which of the following are true about limits of step functions. Functions on the interval maybe where a and b are some real. Firstly, any continuous function on closed interval AB is a uniform limit of step functions. Secondly, any differentiable function on closed interval AB. I think differentiability we should avoid writing closed interval because we cannot differentiate on the boundary points. Is a uniform limit of but in that case of step functions any continuous function on closed interval AB is pointwise limit of step functions next we have any function that is continuous outside a finite set finite I think it should be outside a finite subset of closed interval AB then is a uniform limit of step. Firstly, I would like you to observe that if this first option is correct, suppose every continuous function is a uniform limit of some sequence of step functions, then clearly it will be a pointwise limit as well, because we know that uniform continuity implies pointwise continuity. And also, the second option will also be correct, because if a function is suppose different, we know that, if we define it from R to R, and we know that it is differentiable is in closed interval AB, then obviously it is continuous as well. It is continuous on closed interval AB as well. Because every differentiable function is continuous. And hence again by first option, this will be a uniform limit.
Ma'am, first option, how it is correct?
I'll explain that. I'm saying that if it is correct, then clearly second and third will also be correct. Is this much clear? Suppose, that means if we are able to prove that first option is correct, that will imply clearly second and third option also. So for first option, we'll see. I'll explain how we can construct a sequence of step functions. We'll see how beautifully yet technically complex sequence will construct sequence of step functions that will be converging to a continuous function. Mm. Mm. Yeah, I'll explain it in detail how this construction can be done. It is something like this only, but yeah, you'll see how. Now suppose f be a continuous function. Continuous function defined on closed interval AB. So we'll start with an assumption that our function f is a positive function. Further, we'll take this f to be f plus minus f minus, and f plus and f minus are both positive functions. So eventually we'll get same result for general f as well. So let's start, let's see what happens for the positive case. Okay, so now for each n and k in the set of natural numbers. So we have k, n being a natural number, and k belongs to set of natural number using 0. For each n and k, we define the set E n k by f inverse of the close of the interval close k by 2 to the power n upon k plus 1 upon 2 to the power n. So this is basically the set of points in our domain AB such that the value at these points is greater than equal to k to the power 2n, k upon 2 to the power n, and strictly less than k plus 1 upon 2 to the power n. So can you tell me something about this set E and K? How will it be open, close, interval, finite set? Using the fact that f is a continuous function.
Semi-closed open, I think.
Yeah, it will be interval. That much
Yes,
is clear now. Because f
yes,
is a
yes.
continuous function, we know that preimage of an interval will again be an interval. We don't know whether open or closed because yeah, we don't know whether because our this set is neither open nor closed. So yeah,
Mhm.
I hope this is clear how we constructed this E and K. Next, we'll construct the set Fn. So this is F inverse of close to the power n to infinity. So these are some intervals. Now since F is continuous, we know that this implies these E and Ks and Fn's are all intervals. So on intervals, we can define step functions. We define the function, step function Snx. This is equal to summation k from 0 to 2 to the power 2n minus 1, k upon 2 to the power n characteristic function over the set en k x plus 2 to the power n characteristic function fn at x. Now this might seem complicated, but if you just expand it, you can see that this is equal to 0 times characteristic function en0 x plus 1 upon 2 to the power n characteristic function enkx and so on up to the last point would be 2 to the power 2n minus 1 upon 2 to the power n characteristic function enkx plus 2 to the power n times characteristic function fnx. Now for any x, you can see that, okay, if x is such that our fx is between 0 and 1 by 2 to the power n. Suppose x is such that it is somewhere in between 0 and 1 upon 2 to the power n. In that case, this x will belong to en0. From here, you can see that taking k equals to 0, yeah, this is how it will belong to en0. And in that case, what would be snx?
Zero.
0, because obviously if it can belong to only exactly one enk. Now since it is in en0, then it won't be in any other enk, so yeah, this should be en1. Yes. And this should be en 2 to the power 2n minus 1 x. Now next possibility could be x is such that 1 upon 2 to the power n less than equal to fx, strictly less than 1 upon, this would be 2 upon 2 to the power n, k plus 1, 2 upon 2 to the power n. In that case, we can see that x belongs to en1, and this would imply snx would be
1 by 2 to the power n.
1 by 2 to the power n. So in this way, you can see that if 2 to the power 2 to the power n minus 1 upon 2 to the power n, this is less than equal to fx and strictly less than, because k is up till 2 to the power 2 to the power n, sorry, 2 to the power 2n minus 1. So k plus 1 would be 2 to the power 2n upon 2 to the power n, which is just 2 to the power n. In that case, our x will belong to en 2 to the power 2n minus 1, and snx would be the, basically this would be the
1
lower,
by.
yeah,
Yes.
this would be the lower bound.
These are step functions. No? Oh,
Yeah, yeah, this snx is step function because basically this is a linear combination of characteristic functions. These these
yes.
are characteristic functions. This is a finite linear combination of characteristic functions. So for each n, we are distributing the set of range. Uh, you can see that we are classifying the range set. We are looking for x
Yes.
such that fx lies between 0 and 1 by 2 to the power n. Our intervals are defined using the range of the function f. And since we know that the function is continuous, this range will be, eventually this will be intervals. So in this case, snx would be 2 to the power
This is
2n minus
Lagrange
1 upon.
approach. This is Lagrange approach, no?
I don't know the name. Was it done in the theory lectures?
Yes. In Lagrange integral, that said that in Riemann integration, we divide the domain,
Hmm.
and in the integral, Lagrange
Hmm.
actually divide the codomain.
Range. Yeah.
Yes, range.
Instead of dividing the domain, in this case we are dividing the range or the codomain.
Code. Yeah, yes, range.
And using that we construct this sequence of step functions. Now fx can either be less than 2 to the power n, or it can be greater than 2 to the power n. If it is less than 2 to the power n, obviously it will lie in either of the subintervals, and or else it can be, we have fx to be greater than equal to 2 to the power n, and in that case we know that this Snx would be, this would be 2 to the power n. I hope the construction of the step functions is clear, how we are defining the step functions.
And what about Fn?
What Fn? Yeah,
Well,
for the case fx greater than equal to 2 to the power n, in that case x belongs to Fn. So in that case the value of function Snx would be 2 to the power n.
sorry.
Okay. Yeah, so basically a function can either have value greater than equal to 2 to the power n, or it will be less than 2 to the power n. In this case, x is belonging to Fn, and we know that uh, Snx is 2 to the power n. In this case, this can be in either of Enk, and in all Enks, this is how we define our step function Snx. So I hope the construction of the function Snx is clear. So yeah, basically it also depends on n. So n will give us the number of subintervals. Now we'll see that how this sequence of step functions is converging uniformly to function f. Okay. So now since f is a continuous function defined on closed interval ab, it will clearly be a bounded function. And since f is continuous function defined on closed interval AB, it must be bounded. F is bounded. This implies there exists some n naught in n such that fx is strictly less than 2 to the power n naught for every x in AB. We can find such an n naught because the function is bounded. Obviously, we can take this n naught to be large enough. 2 to the power n naught will be larger, and fx would be always strictly less than 2 to the power n naught. Or we can say that x belongs to E n naught k
For some k.
for some k lying from 0 to 2 to the power 2 n naught minus 1. Obviously, since fx is strictly less than 2 to the power n naught, it will lie in one of the en naught. So,
Oh, yes,
yeah,
yes.
in one of the en naught keys. Or we can say that fx is strictly less than 2 to the power n for every n greater than equal to n naught. This is also true because this is less than 2 to the power n naught for small n capital, for small n greater than equal to n naught. Yeah, everything will hold. And this will imply that x belongs to Enk for some k in k from 0, 1, 2 to 2 to the power 2n minus 1. And this is happening for all n greater than equal to n. This will just help us to prove the convergence criteria. So now since x belongs to the interval E and K, that means K upon 2 to the power n, this is less than equal to fx, strictly less than K plus 1 upon 2 to the power n for some K lying between 0 to 2 to the power 2n minus 1. And this is happening for all n greater than equal to n. That means Snx is equal to K upon 2 to the power n. We can start with some arbitrary x. Yeah, from here we can say that for any x in closed interval AB, this is happening for some k from 0 to 2 to the power 2n minus 1, and this n is greater than equal to n. So this will imply that 0 is less than equal to fx minus snx, and this is strictly less than now
8 by 2
fx,
to the power.
this will be just 1 by 2 to the power n. So I hope this is clear how we are getting this inequality. Just using the above two two results, this one and this one. Combining these two, we get this inequality. Now we can apply, this is happening for all n greater than or equal to n naught. Now everything is independent of k. And now we can apply the
Please theorem.
sandwich theorem. This implies by sandwich theorem, we get the pointwise convergence. Limit n tending to infinity, Snx is equal to fx. And since x belonging to closed interval AB was arbitrary, we get the pointwise convergence. So from here also we can say that the third option is correct because we are getting a sequence of step functions that converges pointwise to this continuous function f. Therefore, we get the pointwise convergence. Hence, our third option is correct. Okay, next we'll look at the uniform limit as well. Let me mark this equation as star. You can observe that this equation holds for any x. So the upper bound and lower bound for fx minus snx are independent of x. That will give us the uniform limit. Also, by star, this mod fx minus snx, this is strictly less than 1 upon 2 to the power n for every n greater than equal to n naught and for every x in closed interval AB. Because this everything else was independent of x. That gives us the, we can take the supremum minus Fnx, x belonging to closed interval AB. The supremum is strictly less than 1 upon 2 to the power n, and hence we get the uniform convergence. Okay. X minus Sn root norm less than 1 upon 2 to the power n, which goes to 0 as n tends to infinity. Therefore, Sn is a sequence of step functions that converges uniformly to the continuous function n. first, and hence the second option are also correct. So what can we say about the fourth option? So in fourth option, the function is not continuous. They're saying that it has some discontinuities at some finite number of points in closed interval AB. So in that case, do you have any idea? Yeah, here also we
Fourth
need to
option
look for,
says that it is continuous outside a finite set of values.
yeah. So what I could see from here, that means f is continuous. Let's say f is continuous in close AB minus some x1, x2, finite number of points, xk suppose. So it is continuous outside finite subset of closed interval AB. So this is what I could infer from the question. And the problem would occur only if the point of discontinuity is the infinite kind of discontinuity. Suppose we have function
Uncountable.
1 upon x in that case, and our domain is from 0 to 2. At 1, we have infinite discontinuity. So yeah, what happens for the general f? Here, everything we had proved for positive functions. For general f, you can see that we can write this function fx to be f plus minus f minus, where f plus is just maximum of f is then 0, and f minus is minimum of this country minus f. So in this case, can you see that this f plus and f minus both are positive functions? Suppose f is some continuous
Yes, yes.
function whose range set contains positive as well as negative values. So are these f plus and f minus continuous as well?
Hmm.
Yeah, suppose our function was something like this. So f plus takes just the positive values, and wherever the function is negative, it will make it 0. Something like this. This is the f plus, and f minus will give positive value because we are taking minus of fx. So yeah, it should be maximum here. So f minus will give us positive value whenever the function is negative, 0 else. Something like that. Yeah, the curves need not be of same length. Something like this. Yeah. So these both these functions are continuous and positive functions. Hence, by case 1, we can find a sequence of step functions for f plus and f minus. Taking their difference, we'll get another sequence of step functions that will be converging uniformly to the function f. Hence, we can prove this for general functions. And for the case of discontinuity, I think there should be a problem only for the case of infinite discontinuity. In this case, I don't think we'll be able to find sequence of step functions. Because if at suppose this point we have a sequence of step functions that is converging to the function f, that means the sequence Sn x naught for fixed x naught, this is tending to infinity. So anyways, at in some interval around x naught, we won't be able to get the uniform continuity because in uniform convergence, because uniform convergence will imply uniform boundedness. Convergent sequence is bounded. But yeah, I would like you to try it yourself, see exactly how we can prove that there will be problem in the case of infinite discontinuity. So was this proof clear? How we constructed the sequence of step functions by dividing them.
It is so many things, and I had done this already. Oh my god.
Yeah, this is quite complicated. That's why I tried to prove everything. But this is a very good result. This result is used a lot of times. And it saves us, na? Because yeah, eventually not just for continuous functions, we can construct sequence of. So these are step functions. Then we have simple functions. For step functions, we need our domain, these E and Ks, this to be intervals. Further, we can define simple functions where the functions are linear combination of characteristic functions defined on some measurable sets. And using that, we can expand the range of integrable functions. So that's how we uh, integrate various other functions that were very difficult to integrate if we followed the Riemann integrability condition. Okay, so let's move to next question. Let I be some unbounded domain. And f is from some function from I to R, be a function first point says that if f is greater than equal to 0 almost everywhere, greater than equal to 1 almost everywhere, then f cannot be integer. Second point, if f restricted to close interval minus n to n intersection I is integrable on the domain minus n to n intersection I, is Lebesgue integrable for each n and n, then f should be integrable over I as well. Third point, if f is Lebesgue integrable over I, then f restricted to closed interval minus n to n intersection I, this is integrable over closed interval minus n to n intersection I for every n and n. Fourth point, if f is Lebesgue integrable, then this implies mod f is Lebesgue integrable. So let's look at first option. So any idea? Should the function, if suppose f is some function which is greater than equal to 1 almost everywhere. So by almost everywhere, we means fx, this is greater than equal to 0 for every x in some x, which is a subset of I, and this x is a subset of I such that measure of the set I minus x, so whatever is left outside x has a measure 0. So basically the function f is greater than equal to 1 outside a set of measure 0. That's what we mean by almost everywhere. We are saying that our function is greater than equal to 1 almost everywhere in I. I is an unbounded domain. It's an unbounded interval. So they are saying that it cannot be integrable.
Hmm. Then there is a theorem we can use that
Which theorem?
which says that if f and g are two Lebesgue integrable function on I,
Hmm?
and if f is greater than equal to g almost everywhere on I, then integration of f is greater than equal to integration of g.
Yes.
So here
Now
we take g to be 1.
we can take some other function gx to be equal to 1 for every x in I. This will imply f is greater than equal to g almost
Almost.
everywhere. And from here, using the result, we can say that this integral f would be greater than equal to integral I. And this is equal to I1 dx. This is just, now since I is an interval, this would be measure of I.
It will in
What do
some
we, and since I is an unbounded interval, interval f cannot be integrable over I because this is infinity. So integral is greater than infinity. Therefore, the first option is correct.
correct.
Okay. So next we have, if suppose f is integrable on close interval minus into an intersection I for every. So basically, we can say that if we can split our whole domain into some bounded sets, and we are saying that f is integrable on each of these sets. So would that imply the function is integrable on the whole domain?
We have the converse part of it.
Yeah, yeah, converse will be true. So in this case, we can just give an example to show that this is incorrect. If we consider I to be the set of real numbers and I take fx to be equal to 1 for every x in I. So this would imply that minus n to n intersection I is just minus n to n fx dx. This is just integral minus n to n 1 dx, which is n, which is always finite for every n in n. But clearly, since the measure of the set R is not finite, we get the contradiction. This implies f belongs to L minus n to n intersection I. Yeah, in order to contradict something, we can give an example, but we cannot do it to prove. While we are proving something, we cannot use examples. Here we are just discarding the option, hence we can use examples. But this integral over R fx dx, or instead of R, you can take 0 to infinity. So this will be measure of R, which is, or we can say, which is not finite. Instead of equal to infinity, just this implies f is not integrable on whole interval I.
So you're saying not finite is more correct. I think
Yeah, equal to infinity you should always avoid writing something like this. While saying that something is finite, we say that this is less than plus infinity, and when it is not finite, you can just write it something like equal to infinity will lead you to some other issues. Okay. Next we have converse part. So we know that our function f is integrable over an interval, which is an unbounded interval. We need to show that it will be integrable over its subsets clearly, or we can say that this f restricted to minus n to n intersection I is nothing but f times characteristic function minus n to n intersection I. Now, since I is an interval, minus n to n is an interval, eventually this is also an interval. So this function is some kind of step function. And obviously, this f is times characteristic function minus n to n intersection I at any point x. This is just multiplication, pointwise multiplication. This will be always less than equal to fx. So
Oh,
yeah. So this will give us, again using the same result, integral over I characteristic function minus n to n intersection I. This will be less than equal to I fx, which we know that this is finite. And integrating this function is over interval I is same as integrating it over minus n to n intersection I, because outside it's always 0. Fx dx, this is that's how we define the characteristic function. So therefore, the function f is integrable over the set minus n to n intersection I for every unit. Hence, the third option is correct.
fourth one is also correct to the
Mm. And this happens for positive functions. Does this happen for arbitrary functions? Or we need f to be positive?
every maximum. Proposition is that if f and g are Lebesgue integrable for I, then maximum of fg, minimum of fg, f plus f minus, and mod f. These are
Okay.
also Lebesgue integrable.
Hmm. So how will that
Only,
be useful?
only f should be Lebesgue integrable.
Yeah. In order to prove this third part, I couldn't understand what you're saying. Please repeat.
Third one. Third or fourth?
So,
No.
okay, so you were giving the explanation for fourth part, na? So I was asking whether this condition holds for arbitrary functions or we need the function to be positive. So if the function contains negative values as well, suppose it is negative outside this interval, and in that case, our new function would be 0 here. Yeah, this inequality holds only for positive functions. Are you getting my point? Yeah, suppose this is minus n, our function is negative here. In that case, this x times characteristic function would be 0. Something like this. Suppose n is here. So it will be like this. So in this case, the function is getting bigger. So yeah, this holds. This is holding only for positive functions. And for arbitrary functions, we'll again use the fact that f is equal to f plus minus f minus. So yeah, while proving, we should start with the function positive. This happens for positive functions. And then we say that if when f is not positive, we can write f to be equal to f plus minus f minus. Now, since f plus and f minus are positive, also, since f is Lebesgue integrable, f plus and f minus will also be Lebesgue integrable because we know that maximum of two functions, when both are integrable, the maximum is also integrable. Also, f plus, which is just maximum of f and 0. This is integrable over I because f and constant function both are integrable, constant 0. And f minus, these both are integrable over I and positive as well. This implies by case 1, f plus is Lebesgue integrable over I intersection minus n to n, and f minus, this is Lebesgue integrable over I intersection minus n to n. Now we can use the fact that f is equal to f plus minus f minus, so f will be integrable as well. So I hope this is clear how we prove such results. We start with positive functions because this inequality star, this relation we had only for positive valued functions. Then for arbitrary valued functions, we take this f to be equal to f plus and f plus minus f minus. And since f plus and f minus both are positive valued functions, hence we get the same result. Also, we know that if two functions are integrable, then maximum of both and minimum of both is also integrable. So yeah, now you can tell me what you were saying about the fourth option.
Fourth option is direct.
There also we can use the same thing, no? Because yeah, this also I'll explain. Now since f is integrable, as we have proved above, f plus and f minus will also be integrable, and we can write mod f equals to f plus plus f minus. You can verify this. Any arbitrary function, we can write it as f plus minus f minus, and its modulus is equal to f plus plus f minus. Basically, whenever it is negative, this f plus will be 0, and f minus would be the negative,
Negative of the
positive part of
negative.
negative. Yeah. So eventually, we can write modulus in this form. Now, since both the functions f plus and f minus are integrable, so mod f will be integrable as well. So therefore, this fourth option is also correct. So eventually, in this case, first, third, and fourth were correct. Second was incorrect. Okay. Next question. Let f and g be some functions defined from I to R such that they are equal almost everywhere. Then, if f is Lebesgue integrable, this implies g is Lebesgue integrable, but the integral need not be same. Then we have if f is upper function, I'll write it f belongs to ui, then that would imply g belongs to ui. That means f is an upper function implies g is an upper function as well. Next we have f is Riemann integrable. That implies g is Riemann integrable as well. Either both are Lebesgue integrable or none of them is. Okay. So let's recall what do we mean by so exact definition when we say that a function is Lebesgue integrable. If f is a function from I to R, we say that f is Lebesgue integrable if I can find functions u and v who upper functions u and v such that integral over I, sorry,
F
such
equal
that
U
this
minus one.
f is equal to u minus v, and this is happening for I think it's for almost everywhere.
Yes.
And what do we mean by these upper functions? This is a class of functions that are, can you tell me the exact definition?
Which ma'am?
Definition for when do we call a function is is an upper function? Real valued function f
A real valued function f from I to R is called an upper function if we can find an increasing sequence of step functions Sn such that
that
Sn
converges to
increases to f almost everywhere and the
and
integration of Sn n tending to infinity is finite.
the sequence of integral is finite. Is called
Then f is called upper
upper function
function
if there exists a sequence, say Sn, of step functions such that Snx is converging pointwise. In fact, it is a monotonically increasing function and it is tending to fx. I should write Snx. Snx this increases to fx almost everywhere. That means for each for almost every x, Snx is an increasing function, as is an increasing sequence that is converging to fx. And uh, the sequence,
integral of
integral of Snx. This is a sequence of
integrals.
so basically this is a sequence of real numbers. Eventually this integral is a real number. is a sequence of real numbers, and this is convergent. In that case, we say that the function f is an upper function. So, in order to check whether whether a function is Lebesgue integrable or not, we should see if we can write it in this form: f is equal to u minus v, where u and v are upper functions. Okay. So now suppose we'll start with the first part. First part says that if f is Lebesgue integrable, then g should be as well. Suppose f is Lebesgue integrable, f is equal to g almost everywhere. We'll use this later. This implies there exist two upper functions, u and v, such that f is equal to u minus v, and integral over I, f is equal to integral over I u minus integral over I v. Now, since g is equal to f almost everywhere, this implies gx is equal to fx for every x belonging to our domain was I minus some x, where measure of x, this is equal to 0. Okay, so instead of x, I'll write it n, some null set kind of thing. Now this implies, and this is also almost everywhere. So from here, fx, this is equal to ux minus vx for every x belonging to I minus some n1, where this n1 has 0 measure. I'll take this as n2. Now this implies gx is equal to ux minus vx for every x belonging to I minus
n1 union
union, n1 union n2. Now, since both have measure 0, their union will also have measure 0. That means g is almost everywhere equal to u minus v. This implies g is equal to u minus v almost everywhere, since the measure of set n1 union n2 is 0. And again, since u and v both are upper functions, eventually the function g is integrable. Since u and v both are upper functions, this implies g is integrable. G is Lebesgue integrable. And this integral over I, g, this is equal to integral over I u minus integral over I v, which is equal to the integral of function f. So from here, we can see that our first option is
incorrect.
Incorrect, because the integral should be equal. First is incorrect. And we can apply this similar process to prove that if g is integrable, then f should also be integrable. Similarly, we can see that if g is Lebesgue integrable, this implies f is Lebesgue integrable as well. Therefore, g is integrable if and only if f is integrable. And hence, our fourth option is correct, which says that either both of them are integrable or none of them is. Because yeah, if one of them is integrable, then that would imply the other one will be integrable as well. So I hope this first and fourth options are clear.
Yes, ma'am.
Okay. So what can we say about third, Riemann integrability? Any idea? Yes.
If we take fx to be 0 on interval 0, 1
Hmm.
and gx equal to 1 at every rational and 0 at every irrational on that interval,
So we are
then g
taking fx to be 0 for every x in closed interval 0 to 1 and gx to be
1 at rationals
1 for x belonging to q intersection 0 to 1
0 everywhere.
and 0 in q complement intersection 0 to 1. That would imply that fx is equal to gx
Almost
or
everywhere.
in fact not equal to gx. This is happening if and only if x belonging to q intersection 0 to 1. And since measure of the set q intersection 0 to 1, because we know that the set of rationals has measure 0. This has measure 0. This implies f is equal to g almost everywhere. But clearly, f is Riemann integrable and g is not. This I think we proved in previous lecture, no? Or this g is not Riemann integrable. Therefore, our third option is incorrect. Okay, so
Is there any other approach? No?
no, in order to discard an option, it's always good to find some contradicting examples. While proving, we need to take care of all the results and theorems that we are using. Yeah, let's see the second option. Suppose f is some upper function. This implies there exists a sequence Sn of step functions such that Snx increases to fx almost everywhere, or we can write it to be for every x in I minus some n1, where measure of n1 is
0.
0. And since again fx is equal to gx for every x in I minus n2, eventually we'll get that the sequence Snx increases to gx for every x in I minus n1 union n2. Again, since this measure of n1 union n2 is 0, this implies Snx increases to gx almost everywhere. And since this sequence of integral is convergent, because this was originally generating the function f, so the sequence Sn generates
Also
g, and hence g is an upper function as well. Yeah. So I hope all the options are fine in this case.
Now these things are very clear.
So you should always look for how we are able to apply the basic definitions. You should always go back to basic definitions or the results that had been taught in the class. So eventually everything will be done using those results only. Okay. So next we have next assignment. Let's start with, suppose Fn is a sequence of integrable functions. It converges pointwise to some function f under which of the following assumptions we can conclude that f is integrable? Let Fn be a sequence of Lebesgue integrable functions is such that Fnx converges to Fx. This is happening pointwise. Pointwise. Under which of the following assumptions can you conclude that the function f is integrable as well? Firstly, they are saying that if Fn is continuous. So will it be true? If f is a pointwise limit of a sequence of continuous functions which are integrable as well, on maybe I need not be bounded domain. So yeah, if we have a sequence of continuous functions which are integrable and converging pointwise to a function f, will that imply the function f will be integrable as well? If you remember, we did some example related to this in last session. Where we constructed
Yes,
a
ma'am.
sequence.
We take fx to be 1 at every minus n to n interval.
Yeah, we made some triangles, no? Something like this. Then
Yes.
in last, it was, I think, first problem in the previous session. So in that case, we got a sequence of continuous functions that was converging pointwise to this Dirichlet function, which is equal to 1 on rationals and 0 else. So we can see that by a problem done in tutorial 10th. We know that this is incorrect. And in fact, in that case, the functions were bounded as well. So that would, the same example will help us to prove, say that the second option is incorrect as well. They are saying that Fn is bounded for every n and n. So yeah, this same example will hold here also. Then they are saying if Fn is a monotonic sequence. So if you remember, we have this Lebesgue monotone convergence theorem. In that case, a sequence of functions had to be monotonic as well as positive valued. So if the sequence is not positive valued, because we don't know, our codomain is not specific in this case, we might get that our sequence has some negative values as well. In that case, the function f need not be integrable. I'll I want you to search for some example. Look for some
Ma'am,
example.
what you said that monotone is there in the Lebesgue dominated convergence theorem.
Not dominated. Lebesgue monotone convergence theorem. We had a monotone convergence theorem as well, no?
Yes, yes.
Yeah, in that case, we need the sequence to be monotone as well as positive valued. But in this case, we don't know whether the range is to be specified. So yeah, you can look for some sequence where there might be some problem due to this range. Look for some example contradicting this point. Next, they are saying that this Fn is monotonic non-negative, and there exists some function, some integrable function g, such that Fn is less than equal to g for every n in n. So this will be true by
Dominated.
dominated as well as this monotone convergence. See, both of them will hold. So this will be true. Okay, next. This was week 10 or week 9.
This is weak ten.
Okay. Yeah, next we are saying that in the statement of dominated convergence theorem, suppose we replace the dominating function g by some constant. Let's write it. Suppose in the statement what we had that fnx converges to fx almost everywhere. Then the second condition for the monotone, for the dominated convergence theorem is that this fnx is less than equal to some gx, where this gx is some integrable function. Now they're saying that if we replace this g by some constant m, so we are given that this fnx, this is less than equal to some m. Will the result still hold? So if this I was bounded,
Then no problem.
yeah, if I is bounded, then this constant m belongs to Li, and hence again by dominated convergence theorem, everything holds. So that is option, second option, no?
I,
That will give us that the second option was correct.
yes,
Then
and third option
the
is incorrect.
first option says that the conclusion of the theorem still holds. It might not hold if we have some unbounded domain. No?
Mm,
So we look for some example. Suppose fnx was less than equal to 1 for every x, then suppose I was open 0 to infinity. In that case, we can't say anything. It might be convergent, might not be. Okay, and yeah, the conclusion of the theorem never holds, then that also we can't say. Because it might happen that this constant is less than equal to some other function which is integrable. This might happen. No?
mm,
So therefore, first and third will also be incorrect. Next, they're saying that if I is an unbounded interval, then we can always find a sequence fn that is bounded above by m, but yet the function F is not Lebesgue integrable.
Exactly. D and A are related, I think.
D and
A.
A. Yeah, yeah. So if we take, so can you tell me some example?
Yeah, if we take Fn to be 1 when mod x is less than equal to n and 0 outside.
Yeah, so you're taking fx to be 1
Fnx is
when
equal
x
to
when x is in, suppose we
minus
can
n
take
to
minus n
n.
to n. Yeah, and 0 else. So the each of this
So,
fn is integrable.
mm,
If I is unbounded domain, we can find a sequence fn where this each of this fn is in Li, that is bounded
so
above by m. Obviously, it is less than equal to 1, but the pointwise limit. The pointwise limit would be the constant one, which
mm,
is not integrable. Yeah, that's correct. And next one is, which of the following can be deduced from the dominated convergence theorem? Any pointwise limit? Yeah, pointwise limit need not be Lebesgue integrable. That we had seen earlier also, no? The same example for the example that we used, that each of fn is continuous, but the pointwise limit is not the pointwise limit is not integrable. Next is, if fn are Riemann integrable, uniformly bounded, and fn converges pointwise to a Riemann integrable function. This is basically
is correct.
the dominated convergence, na? Because we
It
have
is Raman.
we have
Yes, yes.
uniform boundedness, and the domain is closed interval AB. So
Mm,
eventually that's dominated convergence. Next, we have any pointwise limit of continuous function. Again, that's not possible. The uniform limit of continuous functions is Lebesgue integrable. What can we say about this? They're saying that uniform limit of continuous functions.
domain is bounded, then no problem. But when domain is unbounded,
Exactly. The domain is not specified, na? Yeah. Look for some specific example for this also. Okay. Yeah. Then we had that question related to method of Lagrange multiplier. Even I was not able to solve it. Okay. So were you able to find some solutions? Any idea? So yeah, let's discuss the problem. We are given that f is a function defined on R3 as x to the power k plus y to the power k z to the power k. Then we need to find its extrema subject to the condition subject to x plus y plus z equals to a, where a is some positive real number, k is some fixed positive integer. Okay, then yeah, we need to find its extrema. So basically, we need to find the critical points of the function L, x, y, z. This is equal to x to the power k plus y to the power k times z to the power k plus lambda times x plus y plus z minus a. The critical points corresponding to this function L gives the solution for our constrained optimization problem. So we have del L by del x. This is k x to the power k minus 1 plus lambda equals to 0. This will imply that x is equal to minus lambda by k whole to the power 1 upon k minus 1. We don't know whether this lambda is positive, negative, k is greater than 1 or not. Yeah, k is greater than equal to 1. Okay. Then we have del L by del Y. This is equal to k y to the power k minus 1 z to the power k minus lambda equals to 0. Y to the power k minus 1 z to the power k. This is lambda by k minus lambda by k. And similarly, del L by del Z, this is equal to k z to the power k minus 1 y to the power k plus lambda equal to 0. And from here we'll get z to the power k minus 1 y to the power k is equal to minus lambda by k. So equating these two, we'll get that y is equal to z. Whatever they are, they both should be equal. And then we have del L by del lambda should also be 0. So from these two, we'll get y is equal to z. Then del L by del lambda, this is just x plus y plus z minus a. This is 0. That would imply x plus y plus z should be equal to 0. So eventually, what we have is that x plus 2y, sorry, this is equal to a. So we have x plus 2y, this is equal to a. Then x is equal to minus lambda by k to the power 1 upon k minus 1. So from here, we need to find this values of x and y and eventually z. So at that those points, we need to evaluate the value of function f and see where we get maxima and minima. Basically, I think we'll get just 1 point, but the problem is to solve these equations. So were you able to deduce up till here?
Mm,
From here, maybe we can do one thing, that take some specific a and k, see whether we can discard some options. Just yeah, even this became some very complicated thing because we have power 1 upon k minus 1. Maybe you can try something. Take some specific values of a and k and see if some options. So do you have any idea? Okay. So what is the CS for? You'll try or you have some idea?
okay, I will try, ma'am.
Yeah, because even I'll have to see. I was trying to solve it because, but eventually everything became very complex. So all I could think of is to take some specific values of k and a to look
Mm,
what is happening if we increase or decrease k, how everything is depending on a and k. In that way, we can see which option is correct. Yeah. Okay, we'll try this. Otherwise, yeah, till here. So we are done with week 8, 9, and 10, na?
Yes.
Okay.
There
Week
is a
11.
problem.
Week 11 assignment last date is on 8th. Okay, we'll discuss that in next class. Next class is probably the last session. So if you want something related to theory class or something that you want me to explain, I'll prepare that.
Ma'am, I said on picture 2 problems from week 4, question number 5 and 6.
Week 4. Okay, okay, okay. Okay, I'll see these problems. So week 8, 9, 10 is done. So from some problems from week 4, 6, and 7.
Yes.
Okay, okay, I'll see these one and we'll start. We'll probably if I am able to solve this, I'll start with these problems. And yeah, you also look for this for some specific values of A and K.
Okay.
Okay, then we'll meet next Sunday.
Okay, ma'am. Thank you, ma'am.
Okay.